Welcome to Joe Newton online class. In this video, I want us to discuss this particular topic on the board, which is a topic in physics. The topic is linear momentum. Now, these are the concepts or the basic concepts we are going to look at under this topic. They are impulse, momentum, Newton's laws of motion, that is the first law, the second law, and the third law. The principle of conservation of linear momentum. Now, without wasting time, what do we mean by linear momentum of a body? The linear momentum of a body is simply defined as the product of its mass and its velocity. That's momentum of a body is the product of its mass and its velocity. In other words, or mathematically, we can also say that momentum of a body, that's the linear momentum of a body, is equal to the mass of the body times its velocity. And of course, the unit will be kilogram meter per second from the derivative of the quantities involved in the definition. Okay, now that is linear momentum. Now you should be mindful of the fact that momentum is different from moment. The last time, some time ago, we discussed moment of a force. Moment has to do with the product of a force and the perpendicular distance from its point to the line of action. It's a different concept. But this is momentum. So do not confuse or misunderstand the two concepts. So linear momentum is what we are discussing, which is the product of the mass of a body and its velocity. Good. Okay. Now, what do you mean by impulse? By impulse, it's very simple. The impulse of a body is the product of its what? Its force, that's the average force acting on the body, and the time taken for its action. The impulse of a body is the product of the average force acting on the body and the time taken for that action. That is the impulse of a body. Mathematically, it should be Newton second. Okay, now let's look at it. So the impulse of a body, impulse, is equal to force times time. And the unit of impulse should be Newton seconds. That's the unit of impulse. The impulse of a body is force times time. Newton seconds is the unit because force is in Newton and time is in seconds. Then, but for momentum, we use we use the letter P conventionally to stand for particle momentum of a body. The particle momentum, which is equal to the mass of the body times its velocity. So mass and velocity. And by this implication, the unit will now be kilogram meter per second, because mass is in kilogram and the velocity is meter per second. That's the unit. Okay, now let's look at Newton's laws of motion. Newton's laws of motion. We have the Newton first law. We have the second law. We have the first law. We have the second law. Or have the third law. So these are the laws of motion. Now, Newton's laws of motion. The first law, which is the law of inertia. The Newton's first law of motion states that every body or every particle or every object will remain in its state of rest or continue in its uniform motion in a straight line unless it is acted upon by an external force. So Newton's first law of motion states that every particle or every body or every object will remain in its state of rest or continues in its uniform motion in a straight line unless it is acted upon by an external force. What's the implication of this? It means that when you keep a body or a ball at a position, it remains at rest, that without moving, without motion, unless there's an external force that acts on it. That is it. Or if the body is already moving in a straight line with uniform motion, that is constant velocity. That's what it means. In such a case, the body has no acceleration and it can only alter its motion or accelerate when it is acted upon by an external force. Or it can stop its motion in a straight line when there's an external force that stops its motion. That's the implication of that first law. And that first law, Newton's first law of motion, is known as the law of inertia. What do you mean by inertia? What do you mean by inertia? By inertia. The inertia of a body is the tendency of the body to resist change in momentum whatsoever. That is the unwillingness of a body or of an object to do what? To assume motion when it is a state of rest, or to what? To accelerate when it is in uniform motion in a straight line. That is the inertia of a body. The higher the mass of a body, the greater the inertia of the body. That is the implication of the first law. That is why when you are in a moving vehicle, for instance, that's the application and implication of that first law. When you are in a moving vehicle, for instance, that's why we put on our fasten belt in a moving in vehicles, because in the moving a vehicle in motion, when brake is applied momentarily, when brake is applied suddenly, the person in the vehicle experiences a forward jerk. You jerk forward before you now gather momentum. That because of the relative motion and because of the implication of the first law of motion. In that case, the inertia of your body responds to that sudden brake application. So that's why we have the fasten belt in the vehicles, so that to prevent us hitting the body of the vehicle during that jerking. Thank you. So that is the idea of the first law. Remember, the first law tells us what a force does on a body, that a force can alter the motion of a body, can bring about acceleration, or can set a body into motion, but it does not explain to us how to measure or quantify the force that performs such action. Okay, let us look at Newton's second law of motion. It is this second law of motion that tells us more about how to measure a force and what the unit of force is. So whenever I'm discussing these Newton's laws, I'm very glad, because this is my model in science, Sir Isaac Newton. No wonder my name is Joe Newton. Thank you so much. Okay, now Newton's second law of motion states that the rate of change in momentum of a body is directly proportional to the impressed force or applied force and takes place in the direction of the force. Newton's second law of motion states that the rate of change of a body is directly proportional to the impressed force or applied force and takes place in the direction of the force. That is Newton's second law of motion. Good. Okay, you can see the second law is telling us about about how to determine or quantify force acting on a body, and about the impact of a force on a body. That is what the second law is telling us about. Now, so from the second law now, we have that, from second law here, we have that the force is proportional to rate of change, which is mv minus mu over t. Remember, it says the rate of change, and that rate of change is the time rate of change in momentum, not just the change in momentum itself. So don't make that mistake. So in this case now, this is the statement of the second law. From this statement, we can now go further to derive the unit of force, or the formula for force. Yes. Then from here, I have that for a unit force, we now have that our constant, we have that k, they will give us that k, it gives us km v mu over t. Then for k equals to 1 for a unit force, we now have that F is equals to mv minus mu over t. So from here now, we have that F equals to m bracket v minus u all over what? T. And now recall that A equals to v minus u over t, where A is acceleration of a body. So in this case, when we substitute this A here now, we now have that F equals to what? Ma. And this is the formula for what? Force. From the second law. So the second law, now from the second law, we derive the formula for force. And also from the second law, if you cross multiply here, also from here, we also have that, from here, I have that Ft is equals to mv minus mu. You can see. So still from the second law, we also obtain that the F equals to mv minus mu, which is the what? The impulse on a body. The impulse on a body. Ft equals to what? mv minus mu. In other words, the impulse of a body is also equivalent to the what? To the change in momentum of the body. That is the final momentum minus initial momentum, because mv is final momentum, mu is what? Initial momentum, because v is final velocity, where u is initial velocity. Okay, so that is the second law. So from the second law, and the unit of force is what? The unit of force is Newton. Of course, 1 Newton, which is ascribed to Sir Isaac Newton, my model, 1 Newton is equivalent to 1 kilogram meter per second square. That is mass times acceleration. That is it. Okay, now let's look at the third law, Newton's third law of motion. It's very simple. The third law of motion states, states that to every action there is an equal and opposite reaction. To every action there is an equal and opposite reaction, which means action and reactions are equal and opposite. It's very simple. That is why if you hit your head on the wall, you understand. If you hit your hand on the wall, you understand, because you explain the pain in as much as you give impact to the object which you hit. That is very simple. Okay, so we now look at, it's talking about Fa is equals to negative Fb. That is opposite in direction. To every action there is equal and opposite what? Reaction. Good. Okay, now let's look at the principle of conservation of linear momentum. The principle of conservation of linear momentum. The principle states that in a closed system of colliding objects, in a closed system or isolated system of colliding objects, that the total momentum before collision is equal to total momentum after collision. In a closed system of colliding objects or colliding bodies, the total momentum before collision is equal to total momentum after collision. It means that momentum is what? Conserved in a closed system of colliding objects or isolated system, which means, in other language, in absence of external force, then the total momentum before collision is equal to total momentum after collision for system of colliding objects. That's what it means. Okay, this simply implies that when you have two vehicles, two traveling vehicles, for example, if they hit or collide together, the two vehicles, that their momentum before the collision is equal to the momentum after collision, so it is conserved. And what do we mean by closed system or isolated system of colliding objects? By closed system or isolated system, we mean a system in which there is no net external force acting on the system. So any system in which there is no net external impact or external force acting on it is known as a closed system. That's the language, or isolated system. Okay, now let's look at some equations we get from that. Some equation we can get from that statement. So from the statement, we have that mu plus mu1 m1u1 plus m2u2 is equals to m1v1 plus m2v2. So that's the statement. So remember that momentum is mass and velocity. So from that principle of conservation of momentum, it simply implies that the momentum, this is the body 1 and body 2 symbolized here, that the momentum of this body 1 plus momentum of body 2, you see it, before collision, is equals to momentum of body 1 plus momentum of body 2 after collision. So this one is before collision, after collision. That's it. So that's the statement. But there are separate conditions. If the two bodies are having head-on collision, that they're coming face to face, maybe two vehicles come face to face, they have head-on collision. In this case, they separated, the two bodies separated. But if the two bodies unite after collision, for instance, they have head-on collision, maybe a trailer and a bus, they collided face to face and they move on with common velocity. In that case, now they are seen as united body because they collided and form one body. Maybe the trailer drags the bus and they move on as one body. After the impact or after the collision, we say that they have coalesced, and in that case, they have common velocity. And because they have head-on collision face to face, the equation will change. In such a condition, we have that m1 u1 minus m1 minus m2 u2 is equals to m1 plus m2 times v. So this is a special condition. In this condition, the two bodies have head-on collision, face to face. They are moving in opposite direction, unlike here where they're moving in the same direction. And here, the two bodies united after the collision, after the impact, and they move with what we call common velocity. But here, they separated after the impact and they move with different velocities. So these are the conditions. And some other conditions. Remember, when a body is at rest, the momentum of that body is what? The initial momentum of the body is 0. For a body at rest or a stationary body object, the initial momentum of that body is what? 0. Because the body has no velocity being at rest. So no matter the mass, when you multiply by 0 velocity, it is 0. So be mindful of that point. Thank you. So without wasting time with this analysis, let us take the calculation example on the board to cap up our discussion on this topic. Okay. Now, from this, the question says, two balls of masses, 6 kg and 2 kg, moving in opposite direction. Look at this sentence. Moving in opposite direction with velocities 10 meters per second and 5 meters per second respectively, collide. Then if after the collision, the two bodies coalesce and move in the same direction, calculate the common velocity of the united bodies. Calculate the common velocity of the united bodies. So, in this case, solution, what we have here is the typical case of what I explained last. So, we have that the M1 mass of the first body is 6 kg. And we have that the U1, the velocity of the first one is 10 meters per second. And we are given that M2 is 2 kg. And we are given that U2 is 5 meters per second. Then, and we are told that they move together after the collision. So in this case, we now have, because they are moving in opposite direction, then we now have that M1 U1 minus M2 U2 is equal to M1 plus M2 V. So this is the common velocity, and they move in opposite direction. So, but even that they're moving in the same direction, here will be plus. So be mindful of that condition. So in this case, we have our 6 times our U1 is 10 minus 2 times 5 is equals to our M1 is 6 plus 2 V. So we have 60 minus 10 is equals to 8V. So which is 50 equals to 8V. Therefore, our V equals to 50 over 8. And that will give you 2 here, 25 over 4. And of course, 25 divided by 4, we have 6 whole number, 1 over 4, which is equivalent to 6.25, because 1 over 4 is equals to 0.1 over 4 is the same as 0.25. So that is it. So 6.25 meter per second. So their common velocity, the common velocity of the two bodies when they united after the collision is 6.25 meter per second. So you can determine their kinetic energy if you are asked. Remember that kinetic energy is 1 over 2 mv squared. So it is simple, you can determine that by uniting their masses and then applying the formula. So thank you for paying attention to this particular class and discussion. I believe with this you have understood the concept linear momentum and the other basic concept there, impulse, and the Newton's laws of motion, and the second law, how they led us to the formula of calculating force for an accelerating body. Thank you so much For more of these solutions in mathematics and physics, you do what? Visit my YouTube channel, then like and share, subscribe for notifications. Then for extra classes, online classes through Zoom, Telegram and Skype, you can reach to me through my contact